Jack Paul Energy Invest presents electromagnetic failures in the power industry. Availability of energy is one of the main indicators of the scientific and technological level of development of a modern society. Its increase requires continuous exploitation of new power sources. In this regard, an increase in profitability and reliability of power equipment is a key problem facing the power industry. In a number of cases, a solution to this problem is possible through increasing the purity of feed water. This is obtained through more efficient extraction of contaminating ferruginous impurities, one of the main sources of ferric oxide deposits in boilers and the circulatory sections of turbines. The presence of these deposits has a major influence on the reliability and profitability of thermoelectric power plant equipment. Existing methods of steam counter of thermoelectric power plants cannot avoid the presence of ferruginous impurities, since the relatively pure exhaust turbine steam, after condensation and chemical purification, travels a long way through the pipelines. It proceeds through condensing pumps, low-pressure heaters, deaerators, feed pumps, and only then, after passing through high-pressure heaters, arrives again at the steam generator and turbine. Since practically all equipment and plant pipes are subject to corrosion and wear, condensate in the counter is continuously mixed with ferruginous impurities. Even if the necessary purity is obtained, the micro-impurities that are present in millions of tons of condensate passing continuously through the steam generator quickly deposit a layer of ferric oxide on the walls of the pipelines. This considerably reduces the heat transfer coefficient of the heating surfaces, leading to their overheating and rupture, as well as increased use of fuel and emergency shutdowns of generators. In some cases, for example, when a generator is started and the concentration of ferruginous impurities exceeds the norm by 10 or even 100 times, the increase of deposits intensifies considerably and a purification of counter is necessary. This is accompanied by a discharge of a significant quantity of expensive chemically purified water together with heat down the drain. Impurities, which have partially passed through the steam generator along with the steam, arrive at the turbine and form a deposit on its blades, which causes a pressure increase in the regulating section, an increase in fuel use, and a decrease in profitability. A similar situation exists at thermoelectric plants. Here it is aggravated by the fact that consumers of heat return the heat carrier to the plant so contaminated with ferruginous impurities, products of corrosion of tens, maybe hundreds of kilometers of pipelines. That its discharge and consequent considerable economic loss become inevitable. Unfortunately, the usual methods of water purification are not designed to extract highly dispersive ferruginous impurities and consequently do not produce the desired effect of extracting iron from condensate. However, a solution to this problem is now possible due to the design of electromagnetic filters, EMFs. These have demonstrated excellent service performance where they have been installed. They are compact, simple in operation, and have a high performance range, up to 1,000 and more tons of condensate per hour. Taking into consideration their high efficiency in the extraction of ferruginous impurities, the installation of electromagnetic filters is advantageous at plants that have high ferruginous flows. With current practice at condensing stations, high ferruginous flows occur either in the main flow of condensate after it has passed through a purifying apparatus, or where a flow or several flows arrive at the deaerator. In both cases, the installation of electromagnetic filters is advantageous. A similar situation exists at thermoelectric plants, where purification of condensate in drainage tanks is usually preferred. This means the production condensate returns to the contour and then usually has to be flushed down the drain because it is highly contaminated with ferruginous impurities. So what is an electromagnetic filter? In simple terms, it comprises 4 cases, which are filled with special ferromagnetic filtering granular nozzles. The purifying condensate arrives at the nozzle through the inlet manifolds. Under the influence of a magnetic field created by electromagnets, the ferruginous impurities which contaminate the condensate are deposited on the granular nozzles. The purified condensate continues through pipe bands, returns to the pipeline, and is directed further through the condensate pipe. At the end of the filtering cycle, the nozzle is partially blocked with deposited impurities and requires cleaning. With electromagnetic filters, cleaning is very easy. The filter is switched out of the system by means of valves, and the purified condensate exits through the bypass pipe. Then, the magnetic field is switched off and the nozzle is demagnetized. Nothing then holds the deposited impurities. Within 3–5 minutes, they are washed out by a stream of filtering fluid, which afterwards is directed to a special tank for further purification and recirculation. After that, the magnetic field is switched on again, and the filter is now used again for cleaning. Usually, a regeneration of EMFs takes less than 5 to 7 minutes. Electromagnetic filters are small. For example, an electromagnetic filter of an average output, 500 cubic meters per hour, together with its safety zone, occupies about 15–20 square meters and provides working efficiency in terms of purification of magnetizable impurities of up to 95–98%. Deposition of fractions less than 0.1 microns. Temperature range of purified media up to 500 degrees centigrade. High efficiency of operational parameters. The power consumption is up to 0.4 kilowatts with the filter output at 1 ton per hour. Safe use in premises where the danger of explosion exists, with the use of magnetizing systems with permanent magnets. In conclusion, electromagnetic filters give high productivity and efficiency of purification from ferromagnetic impurities, are small in size and simple to maintain. They offer a successful solution to the challenge of purification in the power industry through reduction of the content of ferric oxide impurities in condensate and feed water of steam generators by a factor of 2–3, decreasing the quantity of ferric oxide deposits on steam generating surfaces. This significantly slows down the rate of corrosion processes, prevents overheating and ruptures of pipelines, improves heat exchange and saves fuel. Electromagnetic filters also offer great opportunities in other industries. Metallurgy. Reduction by 5–10 times of the scale content of circulating and drain waters. Improvement of the quality of hot-rolled wares and the removal of ferric oxide aerosol from the air of industrial premises. Engineering. Elimination of ferruginous wear and treatment products of oils, lubricants and cooling fluids, increased service life of equipment parts and components, improvement of the quality of cooled rolled sheet. Oil and gas industry. expeditious purification of gas and oil products transported over long distances, and the purification of highly dispersive products of pipeline corrosion with minimal hydraulic losses, preventing obstruction of customers' equipment and pumping station equipment. Chemical industry. Improvement of product quality, in particular the reduction of ferruginous impurities by 2-3 times, thus increasing the service life of equipment. Reduction of catalytic contamination and increase in the degree of chemical synthesis by 20-40%. The offshore designs of electromagnetic filters are protected by patents in Japan, Russia, Ukraine, Germany, Sweden, France, the United States of America, and other countries. Check Paul Energy Invest. Welcomes inquiries from interested organizations.